Okay, so welcome to the course Fundamentals of Manufacturing Processes. In week 4, we'll study about metal casting. So, in this part, we'll study about various gating systems and risers, sand casting. So, this course is offered by Professor D.K. Dwivedi from Department of Mechanical and Industrial Engineering, IIT Roorkee, and I'm your TA Alka Jangir from IIT Kanpur. So firstly, we'll be going through some sample assignment questions which will help you in solving your weekly assignments, and after that we'll go through some lecture notes. Okay, so first question is the reconditioned sand used for molding purpose is. Your options are facing sand, baking sand, mold wash or loam sand. So if you know the answer, you can type it in chat, or if you have any query regarding questions or answer, you can unmute yourself and ask. So first question is reconditioned sand used for molding purpose. So out of these, which one would be reconditioned sand? So the answer will be baking sand. So as the name suggests, after baking of the sand, it will be baking sand or floor sand is used for backup facing sand. So along with facing sand, at the face of the mold cavity where the molten metal will first hit, so that part will be having facing sand along with backing sand. So it should have high refractoriness, and it is old and repeatedly used molding sand which is used for the baking purpose, and it is also sometimes called black sand because of the addition of coal dust and burning when it comes in contact with the molten metal. Okay, again, next, other options, there are definitions also given in case the questions is other way around. So in case of facing sand, the face of the mold is formed by facing sand, and the facing sand is used directly next to the surface of the pattern, and it comes in direct contact with the molten metal, and when the molten metal is poured into the mold, it possesses high strength and refractoriness as it comes in contact with the molten metal. Other is loam sand, and it is the type of molding sand in which 50% of clay is present, and it is mixture of sand and clay, and water is present in such a quantity to make it a thin plastic paste. In loam sand, patterns are not used, and it is used to produce large castings. So next question is, in sand casting, parting sand is used too. Your options are increase the adhesiveness between pattern and molding sand, or decrease the adhesiveness between pattern and molding sand, increase the cohesiveness between pattern and molding sand, or decrease the cohesiveness between pattern and molding sand. So your answer will be decrease. Okay, so if you don't use parting sand, what will happen? Your corp and drag, they will attach with each other, and this will ruin your mold cavity that you have formed. Because of this attachment, it might get ruined. So for that purpose, this parting sand is required. It is also sprinkled on the pattern as well for easier removal of pattern. So the parting sand is used to prevent the sticking of green sand to the pattern, and also to allow the sand on the parting surface of the cope and drag to separate without clinging. It serves the same purpose as the parting dust, and parting sand is clean, dry and free of clay and silica, and it is clean clay free silica sand. Parting sand is a type of molding sand that's used to prevent green sand from sticking to a pattern during the sand casting, and it also allows the sand on the parting surface of the cope and drag to separate without sticking together. So between COP and drag, this line it shows parting sand separating COP and drag. Okay, so next question is the main constituent of coarse sand is. So coarse sand is used for making cores. So core is what it is the constituent of the your entire molding, in which it will be used for making hollow castings. Okay, so you'll be putting core which is sometimes made of sand as well. So when it is made of sand, then it is made of which sand? So what will be the main constituent of core sand? So your options are water, clay, silica, binder. So water can be an answer because water can be more the highest amount of amount in the sand. So answer will be either clay, silica or binder. So when you look at the mixture of core sand, it is mainly made of silica and core oil. So as a binder you use core oil. Okay, now in this particular casting, okay, in this particular casting here you can see this is the core. So it is used to make hollow castings. So some part won't be exactly fit. So you can entirely fill it and then drill a hole as well, but uh, that will be that will be adding to your extra work, and also you'll be losing some material. So if a material is precious material or some expensive material, then it might be advantageous. Next up, here this core is held in its position by using chaplets, and this is the core. Okay, so core are the materials which are used to form hollow cavities and projections that cannot be produced by patterns alone. And cores are generally made of sand and can be used to form any complicated contour or cavity. And the cores must be strong enough to withstand the heat and pressure of surrounding molten metal. So this entire white cavity will be filled with molten metal. So it will be exerting some heat as well as pressure on this core sand. So it should have sufficient strength. So core sand requires higher strength than compared to this molding sand. Core print are also used to support cores inside mold cavities where coring is required. The sand which is used to make core is called core sand, and it is also called oil sand. It is the mixture of silica sand and core oil. Core oil is a mixture of linseed oil, resin, light mineral oil and other binding materials. And for the sake of economy, pitch or flowers and water may be used in making of large cores. Next question is, the buoyancy force acting on the core is expressed by, where your PB is force, V is volume of mold, V is volume of core, rho is density of molten metal and small d is density of core material. Now you have to tell which expression will be correct for this force. So the answer will be the second one. Now for this question you just have to remember this formula. So the net force acting on the core is the upward force which acts at the center of buoyancy, and it can be calculated using the equation F net force equals to G. G is your acceleration due to gravity. Capital V is the volume of displaced fluid in cubic meters. And rho aluminum, it is the density of aluminum. Rho core is the density of core. So these densities, if you multiply this with volume, then you will be getting this in terms of kg, right? So it will be ma. Force is equals to ma. So in terms of m, you use density multiplied by volume, and g will be your acceleration. So that way also you can remember this formula. Okay, now in this form you have to remember, like you will be taking which density first. So it will be metals density first and then density of core. Okay, and this exact formula is given here as well. F equal to Vc brackets rho m minus rho c. M is metal, C is core. Next question is, the primary purpose of a runner in a casting mold is to. If you know the answer, you can type it in the chat. So even if you don't know the answer, I'll be knowing like which part I need to tell again. Okay, so your options are: provide non-uniform flow rates of molten metal, feed the molten metal from the sprue base to the gate, and feed the molten metal from the pouring basin to the sprue base, or act as a reservoir for the molten metal. Okay, so which one would be the answer? So runner will be connecting to what? So you need to remember that particular diagram, this diagram, right? So runner will be runner is a channel with a reduced diameter used to allow the flow of molten metal towards the cavity. So it will be connecting this pouring basin to your ingate, right? So it feeds the molten metal from the sprue base to the gate. This one will be the correct answer. So, and feed the molten metal from the pouring basin to the sprue base, these one won't be correct. So these are the definitions of remaining parts of your gating system. So in case of cope and drag, this is the top and bottom part of a casting arrangement, which are called cope and drag respectively. So upper part will be cope. Okay, so and lower part will be drag. Okay, here. So between this there will be parting line, and below part will be drag, upper part will be cope, and they are usually wooden frames. Next you have riser. A riser is often called a feeder. It is a reservoir and a passage included in a metal casting mold to avoid shrinkage of metal. So riser will be having extra molten metal, which it will be continuously feeding, as this casting will keep on shrinking because of solidification. Runner is the channel with a reduced diameter used to allow the flow of molten metal towards the cavity. Next is mold. It is a cavity made out of a pattern. Okay, so firstly you will be making pattern will be having similar dimensions, not dimension, it will be having similar shape. Dimension will be varying because of the allowances that you will be providing to the pattern. Okay, because there will be certain shrinkage, or there can be draft allowance, all those combined will be in case of pattern. So after removing of the pattern, you will be having an empty space where the cavity will be formed. Okay, so that cavity will be filling through the molten metal, and after solidification it will give you the casting. Okay, so it is a cavity made out of a pattern which is mostly made of sand, and the copy of the final desired cast, this will be pattern. Okay, now the core is a sand casting is a device inserted into the mold cavity to create interior features in the casting such as holes. So this is the core, so there will be a hole through, this is going on the both sides, so it will be hole throughout. Okay, so next is gate. So it is the point at which the metal reaches the mold cavity and starts to flow into it. Okay, next is you have to match column 1 with the column 2. So your options are, in case of column 1 you have bottom gate, top gate and step gate. Column 2 has unfavorable temperature gradient, favorable temperature gradient and large casting. So if you have read the definitions for these type of gates, you will be easily knowing one of the things, that step gate is used in case of large castings, and these two, out of these two, bottom gate provides metal from the bottom, that's why it always has unfavorable temperature gradient. So the answer will be first one. So these will be matching in horizontal. Okay, so the definitions for these gates are given here and their figures as well. So in this case, in case of bottom gate, you are using this pouring basin sprue, and after that you are feeding your metal from bottom gate to the mold cavity. In case of top gate, your sprue and all these, it will be providing you directly to the mold cavity. So this pouring basin, it also acts as a riser in this case, because it will be providing molten metal as this mold cavity starts, the liquid metal in this starts shrinking due to solidification. Okay, in case of step gate, if you have very bigger casting, so in that case, to get a directional solidification, you need to provide multiple gates. So this is in case of step gate. Okay, so here the bottom gate has an unfavorable temperature gradient as compared to the top gate, as molten metal is fed into the mold cavity from the bottom, and in the bottom gate, molten metal enters the mold cavity directly without passing through runner in the gating system. The advantage of using a top gate is that mold fills very quickly, maintaining the temperature gradient during the pouring operation. To maintain the temperature gradient, top itself serves as a riser, but is not as effective as the conventional riser system. And in case of a step gate, it is used in the sand casting process for producing heavy casting of large size, and a step gate is used when the molten metal requirement is large and the metal needs to fill the mold cavity in steps using the gate. Next question is, casting yield depends upon. Your options are metal to be cast, complexity of casting, gating system design, and all of these. So your answer will be all of these. So casting yield will be your ratio between the weight mass of the casting to the mass of the entire metal poured into the mold. Okay, so the casting yield is proportion of the actual casting mass W to the mass of the metal poured into the mold, and it is expressed as a percentage as well. Okay, so this will be formula, and it is important to keep the size of gating system small, because it all must be cut from the casting. Okay, so the riser and the pouring basin and all these in this diagram. Okay, so this part and these all part will be cut down after this mold cavity has been filled completely and solidified. Only this part is your casting. So this size of all these should be less, so that your metal consumption will be lesser for the amount of the mold cavity you have used, or the amount of casting you have used. Okay, so it is important to keep the size of gating system small, because it all must be cut from the casting and remelted to be reused. And the efficiency or yield of a casting system can be calculated by dividing the weight of the casting by the weight of the metal poured. Therefore, the higher the number, the more efficient the gating system to the risers. So all these options are correct. So if whatever metal you are using, that will also decide what will be the casting yield, because some metals might have very high thermal conductivity. So in that case, the casting yield is different from other metals. And if you have very complex casting, then also your casting yield might go down. Gating system design, that also changes the casting yield, because the runners and riser, all these must be cut down afterwards. So if the size of those you have taken very larger, then in that case your casting yield will go down drastically. Next question is, in sand casting, the freezing ratio is, your options are ratio of cooling characteristics of riser to casting, ratio of cooling characteristics of casting to riser, ratio of modulus of casting to riser. So modulus is inverse of cooling characteristics. Ratio of solidification time of casting to riser. So one of the answer will be correct. So which one? Second one will be. So you have to remember this particular equation. Okay. So this is freezing ratio, which is area upon volume of casting divided by area upon volume of riser. Okay, so in sand casting, the freezing ratio is the ratio of the casting's cooling characteristics to the riser's cooling characteristics. And the freezing ratio can also be defined as the square of the ratio of the casting's volume to its surface area. And this is known as this rule, which states that the solidification time of a casting is proportional to the square of the ratio of the casting's volume to its surface area. Next question is related to your gating system. Okay, elements of gating system. So you are given this figure and you have to find out which element is A, and your options are sprue, runner, riser and gate. Okay, so you have to figure out what is this element A. Okay, so answer will be riser. Okay, so material will be entering from this side. This is choke, this is pouring basin, and this is the runner, and here this is the casting here. This part is casting, this part is runner, this is choke, and this is the pouring basin. And then after filling the casting, it will go to the riser. So A is your riser. Okay, and this is shown here as well. If it had core, then you can identify core as well. So runner, ingate, this part is cope, drag, bottom board, riser, these all you must remember. Then next, here you have the again definitions I told you earlier as well. So these are the definitions you should remember. These are the elements of gating system. Next question is, according to Keynes' method, freezing ratio X is equal to where? Equal to where these are the definitions. So X is freezing ratio, Y is riser volume divided by casting volume, and A, B, C are constants. So one of the you have to find out what will be the freezing ratio in terms of these constants. So according to Kahn's method, this one will be the answer here. So Kahn's equation is given as X equals to A upon Y minus B and minus C. So here X is freezing ratio, Y is riser volume upon casting volume, A, B, C are constants, and this is the freezing ratio in terms of casting and riser surface area and volume. So surface area upon volume of casting, surface area upon volume of riser. Risers will be here at the down part. So now based on this equation, the relation can be plotted here in the graph. Okay, so after this plot, you can see if your values of these, if it falls in this region, then you will be having a sound casting, and if this ratio is here in this area, then there will be shrinkage present in your casting. So these are optimized using this relation. Okay, now Kahn's method suggests that it is based on the assumption that the cooling rate is linearly proportional to the ratio of surface area and volume, and the riser is used to compensate for liquid shrinkage, and this is the freezing ratio that I told earlier. This is similar to this. Next question is, a cast steel slab of 30 times 20 times 10 centimeter cube is poured horizontally using a side riser, and the riser is cylindrical in shape with diameter and height both equal to 25 centimeter. So freezing ratio is, so freezing ratio you have to calculate. Your options are 1, 1.5, 2 and 2.5. Okay, so for calculating freezing ratio, you should know the area and surface area and volume, these formulas for various shapes. So here freezing ratio you already remember, A upon V upon for the casting divided by A upon V of the riser. Okay, so the volume of casting will be 30 times 20 times 10, so it will be 6000 centimeter cube, and surface area of casting, so it is a cuboid, so the formula will be 2 times LB, BH and LH in, so here it is 2 times entire, then 30 times 20, so by using this it will be 2200 centimeter square. Now similarly you have to calculate for cylindrical riser as well. Okay, so for that D, and here it is given that your cylindrical riser has diameter equals to height. Okay, so based on that you can, if you put those equal, then you will be getting A upon B in terms of 6 upon capital D. Okay, and D is already given 25, so it will be 0.24. Okay, now you can calculate freezing ratio, it will be around 1.529. Next question is the freezing ratio of a cubical casting whose side is 25 centimeter and a cylindrical riser whose height is 25 centimeter. So diameter equals height, and according to Kahn's method will be 0.5, 1, 1.5 or 2. So you have to again calculate freezing ratio. So freezing ratio was again S upon V casting, S upon V riser. Okay, so for the area of casting, it's cubical, so 6a square will be the surface area and a cube will be the volume, right? So 25 multiplied by 25 multiplied by 6 will be your surface area, and volume of casting will be 25 cube. For surface area of riser, it will be the two faces and one entire perimeter region, and volume of riser will be pi r square h. So using those formulas you can calculate this, and then on calculating this freezing ratio it will be around 0.999 or something, so it will be approximated as 1. Next question is, a big casting is to have a hole and to be produced by using a core of 10 centimeter diameter and 200 centimeter loom. So the density raw metal is 0.077 Newton per centimeter cube and density of core is 0.0165 Newton per centimeter cube. What is the upward force acting on the core prints? Your options are 200, 1100, 950 and 350. So answer will be 350. So this formula also we have studied earlier. Okay, the force acting on core, it will be volume times the density, right? So volume of core times density of metal minus density of core. So these you have to calculate using this geometry of the core. So pi r square h will be the volume. Okay, so using that you can calculate this VC core volume, and then rho c and rho m is already given. So based on this formula you will be getting value of 950.32 Newton. So this will be the correct answer. Next question is, what is the purpose of a pattern in the casting procedure? Your options are to clean the mold before casting, to pour molten metal into the mold cavity, or to create the mold cavity, or to remove the casting from the mold. So your answer will be the purpose of pattern. Pattern will be to create mold cavity. Okay, to remove casting from the mold, this is the process called ejection, and to pour molten metal into the mold cavity, this will be the ladle, and to clean the mold before casting, this is another process. This is also not a reason for using pattern. So casting pattern procedure. So the pattern is a replica of the object to be cast, used to form the cavity in the sand, and it is a crucial element in the casting process as it determines the shape and size of the final cast product. And the purpose of a pattern is, the primary purpose of a pattern is to create the mold cavity where the molten metal will be poured, and the pattern is placed in the sand to create an impression, and it forms the mold cavity. Once the pattern is removed, the cavity retains the shape of the pattern, ready to be filled with the molten metal. Now there are some fill in the blanks type of questions. So first question is, to stop the debris from going into the main casting cavity, blank is used. So for this, skim bob is used. Okay. Next question is, chillers are used in casting too. These are used to increase cooling rate of molten metal and to provide a directional solidification. Okay, so that your casting doesn't solidify before riser. Next question is, which of the following components feed the molten metal to casting setup? So answer will be riser. No, it will be ladle. So from the ladle you will be feeding molten metal to the cavity. So the after shrinkage, if it was defined, then it would have been a riser. Next question is blank sand used in casting contains up to 50% clay. So the answer will be loam sand. Okay. Next is parting line is in between. Your so parting line is always kept in between cope and drag. Next is blank is a virtue by which molding sand permits the escape of gases formed during casting. So because of the porosity that is there in between the sand particles, that is a particular property called as permeability. So that is the virtue by which molding sand permits the escape of gases. So there should be sufficient permeability in sand for the sound casting. Next question is blank is used to minimize splash and turbulence when metal is flown into a downsprue. So this is the pouring basin and strainer and all this. So these all you should remember. So 7th question will be pouring cup is used to minimize splash and turbulence when metal is flown into a downsprue. Now we'll go through some lecture notes, so which will be helping you in solving your assignment. So first lecture is sand molding. Okay, so sand molding in previous class also I told this. So firstly you have mold characteristics. So these all are related to the sand. So your sand should have good permeability, good strength, good refractoriness and good collapsibility. And what all these properties mean, those are given here. So firstly, permeability of sand depends on the average size of the pores and it is related to the distribution of particle size, particle shape and soil structure. Okay. And sand, so it can have green strength, hot strength and dry strength. So these are the definitions of all these. So in previous assignment also I think you were asked questions related to these strengths. So in case of green strength you have moisture present in it. So green strength is the ability of sand to retain its strength, structure and shape while a mold is freshly made and full of moisture. And second is dry strength. So dry strength is the strength of the mold after the moisture evaporates after molten metal is poured into the green mold. Hot strength is the strength of mold after mold gets heated up and is at peak temperature. Now next property is refractoriness, which is the ability of molding sand mixture to withstand the heat of the melt without showing any signs of the softening or fusion. Next is collapsibility. It is the ability of molding sand to collapse after solidification of molten metal. So for the easier removal of casting from the mold, this is required, collapsibility. Otherwise your casting also may get damaged in process of ejecting this casting from the sand mold. So after the solidification of molten metal, the sand should get collapsed for free contraction of the metal. Now next is the factors affecting fluidity. So the fluidity is required for materials where for sand molding where you are making some complex shapes. So if the shape is very complex, so entire corner should be filled completely. So for that your material should have good fluidity, and this fluidity also depends on some characteristics of mold and the metal that you are using and the conditions of poured metal. So in terms of metal, so solidification temperature range, so this depends on the alloy composition. For example, if you are taking copper nickel alloy, then if it has a lower solidification range, then it will be having good fluidity compared to higher range, because some portion of your metal will get solidified first and it will show variation in your composition. So some part will be having higher nickel compared to the other part. And next is surface tension. So surface tension will also determine fluidity. So if it has very high surface tension, then fluidity will be less. Viscosity, this viscosity will depend on temperature above melting temperature as well. So how much superheat you have provided. Next is heat content, superheat. So how much heat your metal can hold, that will also depend. Next is mold. So thermal properties of mold. For example, if you have mold which is made of graphite or metal, then it will have less fluidity because your material will get solidified at the edges very fast because of high thermal heat transfer. Next is permeability. So permeability of sand will also decide fluidity. Next, you have surface roughness of mold wall. So surface finish will also decide fluidity of your metal. Conditions of poured metal. So temperature of pouring. So we already covered heat content, superheat. You have to heat your metal to higher temperature compared to molten metal that you are using, melting temperature. So above that temperature you will be providing extra temperature. Next is sand casting. So the term sand casting can be used to describe the final product as well as the process to make sand casting. So it is a metal casting process which is done at a place called a foundry, and it has stayed as one of the oldest processes, and sand is used as a mold material in this metal casting technique. Sand casting is widely used metal casting process which involves creating a mold from a mixture of sand and a binding agent such as clay, and this technique is employed to produce complex metal parts of various sizes and shapes. The process of sand casting is used to create more than 60% of the metal castings we see in our day-to-day lives. Next is sand casting is widely used metal casting process, and a mold is created by compacting sand around a pattern of the desired object. So you will be having a pattern in between, then you will be having sand surrounding it, then you have to use rammer and compact the sand. So the molten metal is then poured into the mold, allowing it to solidify, and after cooling the sand is removed, revealing the cast metal object. And this process, sand casting, is versatile, cost effective and suitable for various shapes. Next is, what is sand casting? So in sand casting, the molten metal is poured into a cavity in a disposable sand mold. So in case of sand mold, you have to these are disposable compared to, for example, graphite dies or metal dies that you use for solidification. So those can be used multiple times, but in case of sand molding, you have to collapse it afterwards and get your casting from it. Okay, so it contains a hollow chamber of the desired shape where it solidifies to create the cavity shaped component. The clay, epoxy, plaster, metal and concrete, they are all examples of casting materials. So next is the casting produced have exceedingly complicated geometries in a wide range of sizes and weights, and the process is often referred to as sand molded casting. The metals with high melting temperatures such as titanium, steel and nickel are suitable for sand casting. So in case of these, sand will be, it has some refractoriness to it, okay, so it can sustain a very high temperatures which are close to these melting temperature of these metals, right. So these can't be used for the metal molds. So these can be only casted using sand casting. The only casting method that works with these materials is this. As a result, the technique is the best option for manufacturing affordable and small parts in the automotive and aerospace industries. Next is sand casting working. So the sand casting is a process which involves creating a mold using a mixture of sand and a binding agent. So first a pattern of a desired object is made and it is pressed into the sand to create a mold cavity. Channels called gates and risers are added for the molten metal to flow and for air to escape. The mold is closed and the molten metal is poured into the mold, and after the solidification the mold is opened and the casting is removed and the excess material is trimmed and the finishing operations are performed. The sand casting is a versatile and cost effective method for producing metal objects of various shapes and sizes. Now the elements of sand casting. So these are various elements which are shown here as well. So first is cop and drag. It is the top and bottom part of the casting arrangement, which are called cop and drag respectively. They are usually wooden frames. Riser is often called a feeder and it is a reservoir and a passage included in a metal casting mold to avoid shrinkage of metal. So in your final casting there shouldn't be any shrinkage, so that is taken care by riser. Next you have runner. So a runner is a channel with a reduced diameter used to allow the flow of molten metal towards the cavity. Next you have mold, which is a cavity made out of a pattern copy of the final desired cast, which is mostly made of sand. Core is the sand casting, which is a device inserted into the mold cavity to create interior features in the casting such as holes. Gate is a point at which the metal reaches the mold cavity and starts to flow into cavity. Next you have base sand. So this is also known as foundation sand and it is the purest form of sand silica. Next you have binders. So it is the glue which holds the sand grains together and is the binding agent. The most common types of binders are clay and water, oil, resin and sodium silicate. Now sand casting process. So there are various steps related to this. So in first step you have pattern making. So before starting to make your mold, you have to make pattern first. And this is the procedure which involves the usage of reusable pattern which has the same dimensions as the desired finished product. To account for thermal expansion or contraction, a pattern is always made larger than the finished product. So you have to provide certain allowances to the pattern. The pattern is provided with allowances like shrinkage, draft, machining, wrapping allowance before adding sand. Okay, so this is the wooden pattern. So first you have to create this pattern and you have to put this in drag. So drag is prepared first before cope. So drag or top mold making. So first you have casting requires a material which can withstand the pressure of liquid metal. It must also be resistant to metal reaction yet fragile enough to be detached from the casting after it has cooled. Okay, so sand is used to make the mold around the pattern. Types of sand casting are, in case sands that are used in casting, these are green sand, dry sand, parting sand and core sand. So in case of green sand, so it is fresh sand. It is mixture of clay and silica sand constituting 18% of to 30% clay and 6 to 8% water, and it is used for small and medium sized castings. Next you have dry sand. One second. Okay, next you have dry sand, which is the composition of this sand is same as green sand, but it is baked in an oven for several hours at a temperature of about 240 degrees Celsius, and it is used for large castings. Next you have parting sand. It is clay free sand added to allow sand particles to be removed freely without sticking to the surface of cope and drag after the process. Next you have core sand. It is also known as oil sand and it is composed of silica sand, linseed oil, resin, mineral oil and other binding components like dextrose, corn flour, sodium silicate, and because of its high compressive strength, it is utilized in the fabrication of cores. So in this step, the drag is filled with the sand and rammed to make the mold. So in this case, you have prepared your drag. Then you will be after this step, you invert this drag and you remove pattern. So the drag is inverted with the pattern in place and the pattern is now safely removed from the mold, and during this step a gate is carved to assist a proper direction to the mold matter. So this formation of this part will act as choke and this will act as runner, your in gate. So this is carved in this sand in this step. So you have inverted your drag and you have removed the pattern. Next is cope or bottom mold making. Then you will be making other part. Okay, so the cope is prepared by ramming sand around runners and risers, and the core is placed and fixed in the drag during this process. This is now ready for assembling. Next you have assembling the cope and drag. So you will be putting these on top of each other. So the cope and the drag rammed with the sand are now aligned properly to assemble the boxes, and these are aligned using pins to lock them in place. Okay, now these are the pins that I used. Next step is preparing for pouring. So the runners and risers and other fixtures are now removed. So previously you had these parts, right? These are made of wood. So these are also removed in next step, and the frame before pouring the molten metal in this step, and after this the mold is allowed to dry, and this brings us to the next step. Next is pouring. So you have made this entire cavity and entire channel connecting this. After that you will be pouring metal. So the metal which needs to be formed to the desired shape is melted and poured into sprue. Okay, which is a funnel like structure, and this is made to flow to the cavity and allowed to cool, and the sand around it holds the temperature without reacting to it. So because of the refractoriness of the sand, it will be holding its initial shape. So your molten metal will fill entirely into this cavity and will start solidifying. After solidification and after cooling of this uh, casting, you will be removing. So this process involves the shakeout and finishing process. This shakeout is done to remove the cast from the mold, and it is just removing the sand particles by tapping, and the finishing process involves various machining process to provide a desired surface finish for the cast. So because of the sticking of the sand particles, you need to clean the entire surface, and there might be some allowances as well, so you need to make sure that you remove those as well by using machining. Next is sand casting defects. Now there are certain defects also related to sand casting. So sand casting defects are characteristics that deviate from the quality criteria established by service and required by design. These are typically caused by defects in the technique and the sand used to prepare the mold. But there are other notable defects in the final cast, and they are listed below. So these are various defects such as blowholes, swelling, hot tear, honeycombing, sand spots, misruns. So misrun will be the incomplete filling of certain cavities, and in detail we'll be talking about these in next week. So in few next lectures we'll be talking about casting defects. So next you have scaps and buckles, red tail, pinholes, cold shut, metal penetration, etc. Next you have green sand casting, which is a popular and cost effective metal casting method, and it involves creating a mold by compacting a mixture of sand, clay, water and additives around a pattern. The molten metal is poured into the mold, solidifying to form the desired object, and the green sand can be reused, making it environmental friendly. Next, so we have advantages of sand casting. So due to its diversity compared to other manufacturing methods, sand casting allows engineers to build complicated parts from a limitless variety of metals and alloys. And casted parts might be as small as few millimeters and grams, or as large as meters and many tons. So there is wide range of variety, and no other method provides the same option to make intricate shapes as sand casting. And the cost of equipment and tooling is low compared to other manufacturing processes. And the scrap produced can be recycled back to make another cast, and it is adaptable and usable for various materials from low to high melting point metals. So as I told earlier, in case of titanium, nickel and steels, this sand molding casting is only method which you can use. So this is also adaptable and usable for various materials. Next is disadvantages and sand casting. So because of their high porosity, so if permeability is not good for certain sands, then there might be a lot of porosity left in the casting, and there might be shrinkage as well. So there are a lot of defects that will be there, and parts are less durable than machined parts. And defects or quality differences including shrinkage, porosity, pouring metal faults and surface defects are inevitable in this process. And also the microstructure that you get from sand casting, it is not always good for the mechanical properties that are required for particular applications. So you always require particular heat treatments, which also adds to the cost. Next is sand casting has a higher level of porosity than casting methods like investment casting and die casting. And if tighter tolerance is required for making with the other parts, a secondary machining process is often necessary. So you require machining as well as heat treatment, which adds to the existing cost. Compared to the cost of materials and tools, processing costs are considerable, and it is also difficult to remove the thin and little section pattern. Now applications of sand casting. As we know, 70% of the metal castings are from the sand casting process, and some of the commonly known sand casting products are parts that are manufactured through this process are pump bodies, bushes, pistons of air compressors, impellers, engine crankcases and oil pans, gears, flywheels and gas and oil tanks. The mining and construction industry, in this case sand casting is utilized in the mining and construction industries to produce equipment components such as crusher parts, dragline teeth, excavator buckets and wear resistant plates. Next we have marine industry. So in this case sand casting is used in the marine sector to manufacture marine engine parts, propellers, boat fittings and other components required for marine vessels. In case of railway, this sand casting is employed in the railway industry to produce components like railway wheels, brake system parts and couplings. Next you have agriculture and farm equipment. So it is used to manufacture parts of agricultural machine including tractor components, plowshares and irrigation system parts. Next chapter we have core and core prints. So core is used in casting and molding processes to produce internal cavities, and the core is normally a disposable item that is destroyed to get it out of the piece, and they are most commonly used in sand casting. Okay, so this is the pattern, and here we can see the in between this. If you want an entire hole, then you require core, or some hollow shape or shape, then also you require core. Now other thing is core prints. So the core print is an added projection on the pattern, and it forms a seat in the mold on which the sand core rests during pouring of the metal. So there are the projections here which are core prints. Now in case of cores, these are used to get the internal cavity in the castings. These are placed into the mold after removal of the casting, and these are made up of sand and are used in permanent molds also, and the cores are surrounded by molten metal and therefore subjected to uh, severe thermal and mechanical conditions. Core sand should be of higher strength than the molding sand, because you can, in this case you can see that this molding sand is coming in contact with hot metal only on the one side, while this core sand will come in contact on the both sides, right? So this should have higher strength compared to this mold sand. So next you have core prints. So core print is an open space provided in the mold for locating, positioning and supporting the core. As we know that density of core made of sand is less than the density of metal being poured in the cavity, so there will be an upward force on the core, and to overcome this defect the core prints are used, and this force and hence core print design will depend on the moldings and characteristics. Now these are various types of cores. In case of green sand core, it is made of green sand. In case of dry sand core, this core is first kept in oven to dry it and to remove any moisture from it. Okay, so this is dry sand core. It will be having very high strength compared to green sand core. Next you have horizontal core. So it is kept horizontally in the casting. Next you have vertical core. It is kept vertically. Next you have balanced core. So it will be balanced in between the casting. It won't be making an entire hole through the casting. Next you have drop core. So it will be kept at a place which will be near this parting line. Then again you have hanging core as well, which is hanged in the casting. Next you have full scale model of interior surface of part, and it is this core. It is inserted into the mold cavity prior to pouring hot metal. The molten metal flows and solidifies between the mold cavity and the core to form the casting's external and internal surface. This may require support to hold it in position in the mold cavity during pouring, and this support is called chaplets. So these chaplets, these look like this. So these are used in this manner to hold this in position, and these chaplets are made of a metal or material which is compatible with the metal that you are pouring. So it is made of, for example, if you are making aluminum, then it will be made of aluminum. And this is the casting with internal cavity. So there is cavity inside it. So there will be inner diameter and outer diameter. Next, now these are the characteristics that are required for the core sand. So your core sand should have high strength to maintain the shape and resist erosion. Okay, and it should also have good permeability so that there isn't any pores forming inside your cavity. It allows hot air and gases to pass through the voids in sand. It should have good thermal stability to resist cracking on contact with the molten metal. It should also have good collapsibility, so it should have ability to give way and allow casting to shrink without cracking the casting. Now again you have various types of chaplets. So chaplets is a metallic support which can avoid the core shifting, and because of the pouring of molten metal, your core can shift if you are not using any support, and it is the same material of molten metal. Okay, now these are various type of chaplets: radiator chaplets, welded riveted chaplets, cast chaplets. Next you have core positioning and supports. So to support the core, a projection made in the pattern is called core print. Okay, so these are the projections here. So you can see these projections here. So these are the core prints. It is used to form a core seat in the mold. Now this is the core, and there are core prints inside the mold. Now core making methods, there are various core boxes. So these are used for making cores. A core box is a wooden or metallic type of pattern and are made either single or in two parts. So these are made, these may be classified according to the method of making the core or shape of core. The common types of core boxes are described below. So half core box, here you can make half core. So this can be made twice and connected afterwards, or you can have half type of core as well. Next you have dump core box. So in this you can make cuboid type of shape of cores. Then you have split core box. So you can, in these type of, you can make an entire circular type of or cylindrical type of core in case of split cores. Next you have horizontal core. So as the name suggests, it is positioned horizontally in the mold and it depends upon the cavity. The shape is prepared, cavity of the shape is prepared, and it is supported at both ends. Okay, so as shown here, it is supported on the both ends. This is the parting line, your sand, mold, core, all these are shown. Next you have vertical core. So its axis is vertical and the two ends are supported in core seats in cope and drag. Next you have shape and positioning. So this is the cover core. So it is supported from above and it hangs vertically in mold cavity, and this type is mostly used if the code casting is to be used to be completely molded in the drag with the help of a single piece solid pattern. Okay, so here it will be hanging from the parting line. So this pattern that you will be using, it will be single piece pattern. Next you have balanced core. It is supported and balanced from one end only. So sometimes chaplets are used. So here you won't be forming a through hole in the casting. So you will be forming some type of shape inside. So these cores will be used. Next you have drop core or stop off core. So tail core, chair core or saddle core. So there are various names. So these are used, these are employed to make a cavity which cannot be made with other type of cores, and to make a cavity above or below the parting line it is used. Next you have gating system. Now your gating system will be combined with the how you are pouring your material through the cavity. So all these elements such as pouring cup, pouring basin, sprue, chalk, well, runner, side riser, blind riser, top riser, these in gates, this casting, these all will be combined in the gating system. Now this gating system refers to the passageway through which molten metal passes to enter mold cavity, and in gating system refers to the channels through which the molten metal flows to the die cavity, and its key objective is to ensure its smooth and complete flow from the ladle to the mold cavity. And to achieve perfect castings, it is important to have a gating system that is well designed. Now okay, these are the various elements. Yeah, these are the definitions of these given here. So cope is your top half of the mold, drag is the bottom part of the mold cavity is the gap that is created in mold using pattern, so hollow cavity, that is that. Next you have pouring cup. So from here metal is poured and it is used to minimize splash and turbulence when metal is flown into a downsprue. Next you have sprue. So it is pipe shaped, and from the pouring basin the molten metal, it flows into the sprue. Next you have runner. It is the horizontal hollow channels that connect the bottom of the sprue to the mold cavity. Next you have ingate. It is the region where runner joins with the cavity. Next you have riser. It is the excess metal which is poured in the mold. It flows into these cavities, and these act as reservoirs as the metal solidifies inside the cavity and it shrinks, and the extra metal from the riser flows back down to avoid holes. Next you have again definitions of pouring basin. So here in the figure also you can see this part is pouring basin, then you have sprue, then you have runner, then ingate is the connecting part, you have riser as well, you have ingate, and choke will be below this pouring basin. Okay, so pouring basin acts as reservoir from which molten metal moves smoothly into the sprue. Okay, so pouring basin stops slag from entering the mold cavity by means of a skimmer or skim bob, and the depth of the pouring basin is 2.5 times the sprue entrance diameter for smooth metal flow and to prevent vortex formation. Runner, it is generally located in a horizontal plane, parting plane, which connects the sprue to its ingates, thus allowing the metal to enter the mold cavity. Next you have ingate. So these are the opening through which molten metal enters the mold cavity, and the shape and the cross section of the ingate should be such that it can readily be broken off after casting solidification, and also to allow the metal to enter quickly into the other mold cavities. Next you have choke. So it is also called sprue base well, and choke is that part of the gating system which has the smallest cross sectional area, and it helps in controlling the rate of the metal flow, thus ensuring lower metal flow velocity in the runners and minimizing the sand erosion in runners. Now you have types of gating systems. So these depend on gating ratio. This ratio is A, B, C, ratio between these. So A here is cross section area of sprue, B is cross section area of the runner, C is the cross section area of ingates. Okay, so now all these cross sections, they control the pressure that will be there at the um, casting part. So in case of pressurized gating system, you will be having ratio to be 3 is to 2 is to 1. In case of unpressurized system, it will be 1 is to 3 is to 2. Okay, and in this case, air aspiration effect will be minimum. And in case of pressurized gating system, you will be having the volume flow of liquid from every ingate is almost equal, while in case of unpressurized it will be different at the different ingates due to gravity and other factors. And in case of pressurized gating system, you have smaller in volume for a given flow rate of the metal, while in case of unpressurized you have larger in volume for a given flow rate of the metal. Next you have, as velocity is high in case of pressurized, there will be high turbulence which can occur at the corners. Next, in case of unpressurized, you have velocity is low, so turbulence is reduced. Okay, and in case of non-pressurized gating systems, these are more prone to impurities and casting defects such as porosity. In case of the pressurized gating system, it is also called a choked system or gate control system, and it is suitable for brass, magnesium, aluminum alloys and steels. In case of pressurized gating system, it is best suited for ferrous metal, ductile iron, copper and brass. So there can be question related to the metals that are preferable for pressurized gating systems. Next chapter is casting, yield and riser design. So first you have casting yield. So it is the efficiency or yield of the casting, which is defined as the weight of the casting. So final casting that you have made, the usable part divided by the weight of the total amount of metal poured. So total amount of metal poured will be counted in the riser part as well, runner part as well, pouring basin part as well, which has to be cut down from the casting. Okay, so this is the formula: mass of the final casting divided by mass of the molten metal poured, or it is equal to volume of the final casting to the divided by volume of the molten metal poured. Next you have riser design. So riser is a reservoir in the mold that serves as a source of liquid metal for the casting to compensate for the shrinkage during solidification. The riser must be designed to freeze after the main casting in order to satisfy its function. Okay, so it should freeze at last. So casting should freeze first and your riser must freeze after that. Now, definition of riser, it can be defined as the reservoir for supplying molten metal to the casting cavity to compensate additional molten metal, the liquid shrinkages taking place due to the solidification. And the shape of riser is almost cylindrical, since it takes more time to solidify than the sphere and cube shapes. And next you have conditions for designing riser. So volume of riser should be equals to 3 times shrinkage volume of the casting. Solidification time for riser should be greater than or equal to solidification time for the casting. Next you have modulus of riser should be greater than modulus of casting. Modulus is inverse of the your cooling characteristics. So cooling characteristic is given as area divided by volume. Okay, so here it is given by inverse, so volume upon area of riser should be greater than volume upon area of the casting. So by modulus method, your modulus of riser should be equals to 1.2 times the modulus of casting. Next up, again with the definitions. So firstly, the riser is a reservoir of molten metal which is provided in the casting so that hot metal can flow back into the mold cavity when there is a reduction in the volume of metal due to solidification. The riser must stay in liquid state at least as long as casting and it must be able to feed the casting during this time. In casting process, there are mainly two types of risers which are used. First is open riser, which is it can be top riser, blind riser, side riser. The top riser is placed at the topmost point of the casting so that molten metal can rise up to the highest point of the casting. Next, you have the top surface of the riser will be open to the atmosphere. Hence, we can visually check filling up of the mold cavity. So, in this case, such as these types of systems, here you will be pouring your metal, and after entire filling, you can see the molten material appearing on this side. Then you will be knowing the entire casting has been filled. Entire mold cavity. Next, in case of blind riser, it is completely enclosed in the mold and not exposed to the atmosphere. So it has advantage that when it is inside the sand, so it has lesser chance of solidifying previous than the casting. Okay, because there is no heat transfer, proper heat transfer. Blind risers maintain heat longer than the open risers. Okay, so these are their advantages. Next, you have chills as well. So chills are metallic objects which are placed in the mold to increase the cooling rate of the castings to provide uniform or desired cooling rate. Chills are provided to improve directional solidification, and the material of the chills should be the same as the casting material. Now, solidification of casting. So here you have entire liquid, then solidification starts from the walls, right? So because of walls are already cool, so there will be heat transfer higher at that point. So the solidification will start at the walls, then it will move inwards. So last solidification will be inside. So there will be void formation might be there because of shrinkage. Okay, so during solidification metal experiences shrinkage which results in void formation, and this can be avoided by feeding hot spot during solidification, and risers are used to feed casting during solidification. Now risers are added reservoirs designed to feed liquid metal to the solidifying casting as a means for compensating for solidification shrinkage. So riser must always solidify after casting, and the riser should be located so that directional solidification occurs from the extremities of the mold cavity back towards the riser, and the thickest part of the casting, so it will be solidifying at the last, so it will be compensating the most of the solid shrinkage. So your riser should be at above the thickest part, so the last to freeze this thickest part, so riser should feed directly to these regions. Now why we use risers? So the shrinkage occurs in three stages: when the temperature of liquid metal drops from pouring to freezing temperature, and when the metal changes from liquid to solid state, and when the temperature of solid phase drops from the freezing to the room temperature. So the shrinkage for stage 3 is compensated by providing shrinkage allowance on pattern, while the shrinkage during stage 1 and 2 are compensated by providing risers. Okay, so shrinkage during liquid shrinkage will be compensated by risers, while solid shrinkage will be compensated by pattern allowance. So your pattern will be made bigger compared to the required cavity. Now, based on their location, risers are divided in various types. First is you have top riser. So top meaning it will be at the top of the your mold, right? So in this case, riser is located on the casting. Side riser, so riser is located next to the casting. Okay, so it will be near the casting, it won't be on the top of the casting. Okay, so as shown here, so above the casting, then it will be providing, due to gravity it will be keep on providing liquid metal, and the solidification will start from the upwards. And there are blind risers as well. Blind riser meaning it will be inside the sand, so it will be having a advantage of low heat transfer. So this metal won't be solidifying very fast compared to open riser. Next you have open riser. Open riser meaning it will be open to the environment. Next is solidification time for casting. So solidification of casting occurs by losing heat from the surfaces, and amount of heat is given by the volume of casting. So cooling characteristics of a casting is the ratio of surface area to the volume. So we have studied about the freezing ratio a lot of times. So in case of freezing ratio, you always divide cooling characteristics of casting divided by cooling characteristics of riser. Okay, so higher the value of cooling characteristics, faster is the cooling of casting. And this rule states that solidification time is inversely proportional to casting characteristics. So your solidification time is given as K times volume upon surface area square. Okay, so here your TS is solidification time, surface area is SA, V is volume of casting, K is mold casting. Okay, and K will be your mold constant. Now in case of Keynes method, you have this equation which is x is equals to A upon y minus b and minus c. So here A, B, C all are constants, and capital X is freezing ratio, y is riser volume and divided by casting volume. Okay, so freezing ratio can be again given as surface area of casting divided by volume of casting divided by surface area of riser divided by volume of riser. Okay, so now based on these, when you plot a graph between freezing ratio and volume of riser divided by volume of casting, you can get this type of line. Now based on this, you optimize your conditions. So if for your particular casting design, if your characteristics fall in this region, then you will be having sound casting, and if you are in this region, then you will be having shrinkage in casting. Next you have modulus method. So in this case, modulus is simply inverse of the cooling characteristic. Okay, so modulus is the inverse of the cooling characteristic, which is surface area. Cooling characteristic was surface area upon volume, and it is defined as volume upon surface area. So in steel casting, riser with height to diameter ratio of 1 is generally used, and the volume of cylindrical riser will be pi d cube upon 4, and surface area will be pi d square upon 4 plus pi d square. Okay, and the modulus of such cylindrical riser would be 0.2 times d, since mr is equals to 1.2 times mc, so your d will be 6 times the mc. M is modulus of casting. So for sound casting, modulus of riser should be greater than the modulus of casting by a factor of 1.2. Now for pouring time, it is the time required for filling the mold in pouring time. So too long pouring time can cause higher pouring temperature, and too less pouring time will be having turbulent flow and defective castings. And it also depends on casting material. So whatever casting material you are using, based on that also you change your pouring time and complexity of casting, section thickness and casting size. Now pouring time is calculated by empirical formulas obtained by experiments which differ from one material to another and one casting to another. For non-ferrous materials, long pouring time would be beneficial since they lose heat slowly and also tend to form dross if metal is poured too quickly. Effective sprue height. So effective sprue height H of a mold depends on the casting dimensions and type of gating system. So it can be calculated using following relations. Okay, so for effective sprue height, capital H of a mold depends on the casting dimensions and type of gating system, and it can be calculated using following relations. So for top gate, your capital H will be equal to small h. Small h is the size of this entire sprue up to here. Okay, and C will, here small h is sprue height, small p is height of the mold cavity in cope, and C is the total height of the mold cavity, so considering drag as well. So values of H, P, C are shown in the for various gating systems. Okay, so here in case of bottom gate, you'll be having H equals to small h minus C upon 2. In case of parting gate, you will be having capital H equals to H minus P square upon 2C. Next, the choke area. So in this, it is the main control area which meters the metal flow into mold cavity. So normally this area happens to be at the bottom of the sprue, so sprue should be designed first, and having sprue bottom as the choke area helps in establishing proper flow in the mold easily and early. Okay, so with this, notes are completed. I'll be going through a sample assignment questions once again for those who joined late. Okay, so first question was, the reconditioned sand used for molding purpose is facing sand, baking sand, mold wash or loam sand. So the answer was baking sand. So in this case, you have, in case of baking sand, it is used to back up facing sand. Okay, so it is old and repeatedly used molding sand, and it is also sometimes called black sand because of the addition of coal dust and burning when it comes in contact with the molten metal. Facing sand is the face of the mold is formed by facing sand, and the facing sand is used directly next to the surface of the pattern, and it comes in directly contact with the molten metal when the molten metal is poured into the mold. It possesses high strength and refractiveness as it comes in contact with the molten metal. Loam sand, it is 50% of clay, so it is the type of molding sand in which 50% of clay is present, and it is a mixture of sand and clay, and water is present in such a quantity to make it a thin plastic paste. In loam molding, patterns are not used, and it is used to produce large casting. Next question is, in sand casting, parting sand is used too. So your options are to increase adhesiveness, to decrease adhesiveness, or to increase cohesiveness, or to decrease cohesiveness between pattern and molding sand. Answer will be second one. So in between cop and drag, you apply this parting sand for the easier removal of the cop from the drag, and also from pattern from the sand. So the parting sand is used to prevent the sticking of green sand to the pattern, and also to allow the sand on the parting surface of the cop and drag to separate without clinging. It also serves the same purpose as the parting dust, and the parting sand is clean, dry and free of the clay and silica. It is clean clay, free silica sand, and the parting sand is type of molding sand which is used to prevent green sand from sticking to the pattern during sand casting, and it also allows the sand on the parting surface of the cop and drag to separate without sticking together. Next question is, the main constituent of the coarse sand is. Your options are water, clay, silica and binder. So the answer will be silica. Okay, so here in this figure, this part here which will be helping in making hollow shapes, it will be your core. So for supporting this core, you use chaplets, and the prints here will be core prints. So the cores are material used to form hollow cavities and projections that cannot be produced by patterns alone. See, the cores are generally made of sand and can be used to form any complicated contour or cavity. Cores must be strong enough to withstand the heat and pressure of surrounding molten metal, so core sand requires higher strength than molding sand. Core prints are also used to support cores inside mold cavities where coring is required. And the sand which is used to make core is called core sand, and it is also called oil sand. It is a mixture of silica sand and core oil. Here core oil is mixture of linseed oil, resin, light mineral oil and other binding materials, and for the sake of economy, pitch or flowers and water may be used in making of large cores. Now the force acting on the core is expressed by. Your options are given here, so this is the formula. So F net will be equals to G times volume times this rho of aluminum minus rho of core. So rho is your densities of aluminum and core, V is volume of the displaced fluid in cubic meters. Okay, and G will be acceleration due to gravity. Now this can be written in this format as well for the core. Okay, so here Vc times rho m minus rho c. Now the primary purpose of a runner in a casting mold is to. Your options are provide non-uniform flow rates of molten metal, feed the molten metal from the sprue base to the sprue base to the gate and feed the molten metal from the pouring basin to the sprue base, act as a reservoir for the molten metal. So the answer will be this one. So for these type of questions you have to remember this particular figure. So how your molten metal will enter from which part and how it will go from choke to connecting to the cavity part. This will be ingate, this will be pouring basin, pouring cup, then you have sprue. All these you have to remember. Now these are various parts of the your entire mold. Okay, so first you have cope and drag. So upper part is cope, lower part is drag. Riser will be reservoir of the molten metal. So after filling the cavity, your material will go in riser and it will be providing molten material in case of liquid shrinkage. Okay, and then you have runner. So runner is a channel with a reduced diameter used to allow the flow of the molten metal towards the cavity. Mold is the empty space, right? So it is cavity made out of pattern, so which is mostly made of sand. And what is pattern? Pattern is the copy or replica of the final desired cast. Next you have core. So core is the sand casting. It is a device which is inserted into the mold cavity to create interior features in the casting such as holes. Next you have gate. It is a point at which the metal reaches the mold cavity and starts to flow into it. Now you have to match column 1 to the column 2. So you have bottom gate, top gate and step gate. And column 2 has unfavorable temperature gradient, favorable temperature gradient and large casting. So these are the various gates, right? So here you have to understand what each gate means, and then, so for example, in case of bottom gate, it will be separate from the your vertical part, right? So it will be providing metal from the bottom to the mold cavity. So here you will be having unfavorable temperature gradient because your metal will start filling from the downwards here, while in this case your metal will start getting at the lower part, then it will start building up to the this part. So here your pouring basin acts as riser as well, so it has favorable temperature gradient. In case of step gate, you have various steps in gates because of the large size of the cavity. So to maintain this directional solidification, you require multiple gates. So here you will be having large casting. So these are, A will be the correct answer here. Okay, so in case of the bottom gate, it has a unfavorable temperature gradient as compared to top gate, as molten metal is fed into the mold cavity from the bottom, and in the bottom gate molten metal enters the mold cavity directly without passing through runner in the gating system. And the advantage of using a top gate is that mold fills very quickly, maintaining the temperature gradient during the pouring operation. To maintain the temperature gradient, top itself serves as a riser, but it is not as effective as conventional riser system. A step gate is used in the sand casting process for producing heavy casting of large size, and a step gate is used when the molten metal requirement is large and metal needs to fill the mold cavity in steps using the gate. Now next question is, the casting yield depends upon. Your options are metal to be cast, complexity of casting, gating system design, or all of these. So casting yield is the proportion of the actual casting mass to the mass of the metal poured into the mold. So it is important to keep the size of the gating system small, because it all must be cut from the casting and remelted to be reused. Okay, so the efficiency or yield of a casting system can be calculated by dividing the weight of the casting by the weight of the metal poured, and therefore the higher the number, the more efficient the gating system or risers. So all the options are correct here. Next question is, in sand casting the freezing ratio is the ratio of cooling characteristics of riser to casting or casting to riser, or ratio of modulus of casting to riser, or ratio of solidification time of casting to riser. So this formula you have to remember. Freezing ratio, the up part will be having casting A upon V. This is characteristic. If it is told modulus, then it will be volume upon area. Okay, so A upon V of casting divided by A upon V of riser. So in sand casting, the freezing ratio is the ratio of the casting's cooling characteristics to the riser's cooling characteristics. And the freezing ratio can also be defined as the square of the ratio of the casting's volume to its surface area, and this is known as this rule, which states that the solidification time of a casting is proportional to the square of the ratio of the casting's volume to its surface area. Now here in this figure you have to find out what is A. So initially we pour through the pouring cup, sprue, then choke, then these are the ingates, this is cavity, and this is the riser. So your options are sprue, runner, riser, gate, so it will be riser. Okay, now as I told earlier, these are the definitions which are pretty straightforward. So, and this you can either remember through this diagram as well. So here this part is riser. Next question is, according to Keynes method, freezing ratio X is equal to, your X will be equals to which of these? So this one will be the correct answer, A upon Y minus B minus C. Okay, so here A, B, C these all are constants, and X is freezing ratio, Y is riser volume divided by casting volume. Okay, and based on this you plot a graph between these, then you find out in which particular area you have to optimize your conditions for getting sound casting. Okay, next question is, cast steel slab of 30 times 20 times 10 times 10 centimeter cube is poured horizontally using a side riser. The riser is cylindrical in shape with diameter and height both equal to 25 centimeter. So you have to find out the freezing ratio. So freezing ratio is pretty straightforward. It is area upon volume of casting divided by area upon volume of riser. Okay, so for these various geometries you need to remember various formulas for the surface area as well as volumes, right? So after calculating volume and this area, you can find the answer will be 1.5. Now next question is also similar. Here you have freezing ratio of cubical casting whose side is 65. So cubical, here you have to, surface area will be 6a square and volume will be a cube. And for this riser again you have cylindrical part, so you can calculate and find out freezing ratio will be 0.99, so it will be approximated as 1. Next question is, a big casting is to have a hole and to be produced by using a core of 10 centimeter diameter. Okay, so and 200 centimeter long. The density of metal is 0.77 Newton per centimeter square cube, and for core it will be 0.0165. Okay, so what is the upward force acting on it on core print? Okay, so the formula was given earlier, so you have to find out volume of casting. Okay, you have to find, you already know the densities of metal and this density of core, so these are given here. You have to just calculate this volume of the casting. Okay, so based on that you can find out it will be 950 Newton. Next question is, what is the purpose of a pattern in the casting procedure? So your options are to clean the mold before casting, to pour molten metal into the mold cavity, and to create the mold cavity, and to remove the casting from the mold. So answer will be to create the mold cavity. Okay, so in the pattern is a replica of the object to be cast, and it is used to form the cavity in the sand, and it is a crucial element in the casting process as it determines the shape and size of the final cast product. The purpose of a pattern, so the primary purpose of pattern is to create the mold cavity where the molten metal will be poured, and the pattern is placed in the sand to create an impression which forms the mold cavity. Once the pattern is removed, the cavity retains the shape of the pattern, ready to be filled with the molten metal. Now these are various questions. Okay, now first is, to stop the debris from going into the main casting cavity, skim bob is used. Okay, it's, as the name suggests, for skimming. Now then chillers are used in the casting to increase cooling rate of molten metal. So I told it in previous lecture as well. So chillers or chills, they are used to increase cooling rate and to provide directional solidification. Which of the following components feed molten metal to casting setup? So ladle is used for pouring metal. Now loam sand is used for casting, which contains up to 50% clay. And parting line is always between cope and drag. You have permeability. It is the virtue by which molding sand permits the escape of gases formed during casting. Now pouring cup is used to minimize splash and turbulence when metal is flown into a down sprue. Okay, now these are, okay, then we went through these various lectures. Firstly we went through sand molding. So sand casting we studied how it's performed, advantages, disadvantages, applications. Then we went through core and core prints, various methods and their various types. Then we went through gating systems, okay, various elements, various types of gating systems. Then yield, casting yield, so this is simply this formula. Then we went through riser design, so various definitions of riser and how various their designs are optimized, various methods. And that's all from my side. If you have any query, you can ask. Okay, I'll be ending the session here.